Hello guys and welcome to Mega Course. In this algebra video we are going to talk about logic, part 4. This video is going to be the last video about logic. In this video we are going to cover the following points: equivalence, variable, quantifiers, I mean mathematical symbols. Starting with equivalence, let P and Q be two statements. We define P equivalent to Q. This symbol means equivalent. To be the statement having the truth value as. This statement has the same truth value as this statement. It's P implies Q, P implies Q, and Q implies P. The intersection between these two statements, P implies Q and Q implies P, is this statement, P equivalent to Q. Let's see the truth table. In previous videos you should watch, we talked about P implies Q and Q implies P as well, and we discussed the truth table about these two statements. Now let's see the truth table about P equivalent to Q. P is false, Q is false, P implies Q is true, Q implies P is true. P is false and Q is true, P implies Q is true, and Q implies P is false, because something false can give us something true, then this statement is going to be true. But something true giving us something false is false. Continuing, P is true, Q is false, then P implies Q is false. Q implies P is true. P is true, Q is true, P implies Q is true, Q implies P is true. Now let's see equivalent. We said that equivalent, P equivalent to Q, is the intersection between P implies Q and Q implies P. Let's see, we will use this part of the table. Whenever P implies Q is true and Q implies P is true, P equivalent to Q is true. Whenever P implies Q is true and Q implies P is false, P equivalent to Q is false. As we said in a previous video, that whenever both of the statements are true, the intersection between them is true. Whenever P implies Q is false and Q implies P is true, then P equivalent to Q is false. Whenever P implies Q is true, Q implies P is true, P equivalent to Q is actually true. Although P equivalent to Q can be written as P is true if and only if Q. Here in this sentence, I mean, P is true. They say that P is true. The statement P is true if and only if Q happens. The second statement, the second sentence, I mean, sorry, P is necessarily and sufficient for Q. P is important and also sufficient for Q to happen. The statement P is necessarily and sufficient for the statement Q to happen. Let's see some properties about equivalences. Not P equivalent to P. Whenever you want to find the negation of a statement P, it's not P. The negation of the negation is actually, it's the statement itself, which is P. Not P enter Q and Q, I mean. Not P and Q, as if not here is this distributive among the P and Q. Not P, not Q. Not P, not Q. But what about the AND? The negation of AND is OR. then we have not P and Q is equivalent to not P or not Q. Another one, not P or Q, the same, but the negation of or is and. So not P and not Q. P enter P is equivalent to P. You should study this. P or Q, sorry. P or P is equivalent to P. You should remember both of these. And P or Q or R, P or Q, take a breath, or R is equivalent to P or, take a breath, Q or R, which means here that we can take those parentheses and put them here, so we can solve this one before this one, then solve this all, as if you're writing math. 2 plus 2 times 2 in parentheses. You can do here, you can do them as you like. You can put the parentheses here, parentheses there, as you like. And also here we discussed it in terms of or, here in terms of and the same. P and Q, take a breath, and R equivalent to P and, take a breath, Q and R. When I say take a breath, you should stop talking for a little bit, then say Q and R to make sure that the people listening to you are knows that there is a parenthesis here. Let's seek now into more harder properties. Let's see. P implies, sorry. P and Q or R is equivalent to P and Q or P and R. Let's see what happened here. As if P is distributive among Q and R, and was in between, and or was inside the parentheses. Now in the second, which is equivalent to the first, and is inside the parentheses, and or is in between. So we have P and Q or P and R. Let's see the next one. The next one is the opposite of the previous one. P or is in between, and is inside the parentheses. So, and P is distributive of course. P or Q, and is in between. P or R. Let's continue. Now let's see this one. P implies Q and Q implies R. Then we have P implies R. Let's take an example about this. Imagine Jimmy has the same length of Joan, and Joan has the same length of Jehan. So here we have Jimmy has the same length as Joan, and Joan has the same length of Jehan. So Jimmy will have, of course, the same length as Jehan. Here we have P gives us Q, and Q gives us R. This will lead us to have P gives us R. P gives us R. P implies R. The same as above, but in a different way. P equivalent to Q, Q equivalent to R. This gives us P equivalent to R. I'm sorry, I mistaken here. I have a mistake here. You got me, of course. P here is equivalent to R. Since P equivalent to Q and Q equivalent to R, so P, this will give us, implies P equivalent to R. P here is equivalent to R. I'm sorry. The next one is a good one. Let's see. I will write it down for it to be simple. We here have not P implies not P implies Q, not take a breath. P implies Q is equivalent to P and not Q. Let's take it simple. We know that not this not, I wrote it as it is. P implies Q, we say it not P or Q. I mentioned this in a previous lecture. You should watch it, of course. This will lead us to, we will have not P. My handwriting is so bad. The negation of or is and the negation of Q is not Q. We know that this is P, and this stays and this is Q. So as it is here, P here, and here, and here we have and not Q, so I have done it correct. Let's erase what I wrote, because my handwriting is so bad. And continue what we have. This one is similar to the above one. P equivalent to Q is equivalent to not P equivalent to not Q. You should remember this. P equivalent to Q is equivalent to not P equivalent to not Q. Now the second point, which is variables. Let me pick up this laser pointer. A proposition may contain one or more than one variable. It may contain one or more than one variable. The truth value of this proposition that contains one or more than one variable depends on the value of each variable it contains. Let's see example. X squared plus 2x plus 1 is equal to 0. I have a statement P, for example, that says x squared plus 2x plus 1 equals 0. Is this statement true? I can't know. I need to know the value of x to know if it's true or not. So this statement, if you have guessed already, is true only whenever x equals minus 1. If and only if x equals minus 1. Put minus 1. Here it stays. Let me pick that pencil. Pen. Here minus 1 square, which is 1. And here minus 2. 2 multiplied by minus 1 and plus 1. 1 minus 2 plus 1 is 0. So this statement is going to be true if and only if x equals minus 1. If you put x equals 1 or 2 or 3, it's not going to be equal to 0. So this statement is gonna be false, a false statement. So here this statement, the truth value of this statement depends on the value of x, which is the variable. Let's continue to another example. X squared plus x plus 1 greater than 0 is positive, So when is this statement true? Here we have variable x. So this statement depends on the value of x. If you haven't already known that true for all x, this statement is true for all x. Why is it true for all x? Because we know that x square is always greater than x. So if you put a negative number, this is going to be positive, and this is negative. So this is greater than this and bigger. So it's always gonna be positive. This is positive. always positive. Or you can find delta, which is b square minus 4ac. This is a, which is 1. This is b, which is 1. And this is c, which is 1, also 1. So you are going to have 1 minus 4, which is minus a 3, which is negative. So whenever delta is negative, this means that this equation have no solution. So it's never going to be 0. It's either positive or it's negative. You can put any number, which is for example 1. It's going to give us 3, which is positive. This means that this equation is always positive, always true, always greater than 0 for all x. It can't be 0 because delta is negative. Let me erase my scratching. Okay, let's continue to our course. Now, what are quantifiers? Let's talk about quantifiers. Quantifiers are used to take the long... Take what? I wrote this and I can't read it. Quantifiers are used to take the lobe. What is the meaning of lobe of long statements? I'll continue anyway. We have this symbol. There exists. This symbol means there exists at least one element. This symbol means there exists at least one element. Quantifiers here are made to make the long statements short and beneficial. Instead of saying there exists at least one element inside this set, for example, you use this symbol. Let's continue to another symbol. This symbol plus I forget the name of this mark in English. Sorry. I really mean it. Sorry. There exists and the exclamation mark means there exists one and only one element. Oh, sorry, my fault. There exists one and only one element. When you see this means there exists one and only one element. Let's continue. Well, while this symbol means for every element inside a set, for example, this element means for every element. For every element. This symbol, I mean, means for every element. Note that the negation of this one, which is for every element, is there exists an element, at least one element. And the negation of there exists at least one element is for every element. Now let's take an example for quantifiers. It's easy, I promise. There exists x. There exists at least one element x. There exists at least one element x that is in the set E, such that A of x is true. I wrote it. There exists at least one element x belongs to E such that A of x is true. Another example, for every element x that is in E, example for E is the set R of real numbers. For every element x, for any real number inside that is belongs to the set R of real numbers, we have A of x is true. See you next time in the next video, not logic. Maybe in another lecture we have analysis or physics. I don't know now. We'll see. Subscribe to our channel and thank you for your time. Bye bye.